In 1944, deep inside Harvard University, a machine weighing 5 tons and stretching 51 feet across a steel frame was switched on. It was incredibly loud, a relentless, deafening clack of moving metal. The mathematician John von Neumann relied on this specific machine during the Manhattan Project to calculate whether implosion was a viable way to detonate an atomic bomb. The Harvard Mark I had no microchips. It was entirely electromechanical. Computations were executed by 3 million connections, 500 miles of wire, and thousands of physical gears and multi-pole relays snapping open and closed. Today, the device strapped to your wrist possesses billions of times more computational power than that 50-foot steel frame. Studying this 80-year-old mechanical calculator reveals how physical limitations drove the creation of computer architecture. The design solutions engineered to make the Mark I function are the direct blueprints for the mobile processors running inside your phone today. We're going to decode the structural difference between von Neumann and modified Harvard architectures, examine the Boolean logic driving the arithmetic logic unit, and look at the origins of the first programming manual. The core engineering problem of the 1940s was figuring out how to build a machine capable of general-purpose automated calculation using only mechanical office parts. As we will see, constraints like paper tape and copper relays forced the creation of specific software tools that remain standard in programming today. The Mark I was not a stored program computer. It could not keep its operational instructions and its data in the same place. To input data, the actual numbers the machine would calculate, human operators had to manually dial in values across 60 sets of 24 physical rotating switches. The instructions telling the machine what to do with that data were fed in completely separately. Operators loaded a 24-channel punch tape into a reader. The reader could only process this tape sequentially. It read one row of holes, executed that single mathematical step, and physically advanced to the next. This diagram illustrates the machine's primary limitation. It had no conditional branch instruction. To repeat a calculation, operators took the paper tape and physically taped the two ends together to form a continuous circle. That physical act of joining paper ends together is the exact origin of the programming term loop. Software engineering began as manual physical labor. This diagram shows the Harvard architecture. It features physically separate storage and signal pathways for instructions and data. Because these pathways are isolated, the CPU can fetch an instruction and access data simultaneously without creating a bottleneck. This block diagram shows the contrasting von Neumann architecture, where instructions and data are stored in the exact same memory space. Fetching both over a single shared pathway means they must take turns, causing a traffic jam known as the von Neumann bottleneck. Modern processors built by ARM or used in x86 computers circumvent this limit by implementing a modified Harvard architecture. This diagram shows the modification.
The system relies on a unified main memory space, but as data moves closer to the CPU, it splits into physically separate Level 1 caches, one strictly for instructions and one for data. To maximize processing speed, modern microscopic chip design artificially recreates the physical separation once found between the Mark I's paper tape and metal dials. The electrically conducting parallel wires that transmit this information between memory and the processor are called buses. The data bus moves the numbers, the address bus locates them in memory, and the control bus regulates the flow. This diagram shows the arithmetic logic unit, or ALU. It is a combinational network that executes the core mathematical and logical operations for the system. This schematic shows how the ALU decides what to do based on a control input called the mode selector, or M. When M equals 0, it performs a logic function. When M equals 1, it performs arithmetic. To perform basic addition, the processor executes a strict Boolean equation. The sum of the output equals input A exclusive OR input B, exclusive OR the carry-in bit. The carry-out bit requires its own equation, A and B, or A exclusive OR B and the carry-in. Because each slice must wait for the previous carry-out, this propagation limits processing speed. Whether an operator is triggering mechanical relays on a 1944 calculator or a silicon gate is opening at a billionth of a second on your laptop, the processor is executing these same foundational Boolean equations.
Drafting these equations required manually punching complex arithmetic operations into paper tape, one line at a time. This was a tedious, inefficient process. Lieutenant Grace Hopper, a mathematician who joined the United States Navy Reserve, arrived at Harvard in 1944 and systematically changed how the machine was operated. This diagram represents Hopper's perfection of the subroutine. Instead of writing out the same complex math equations repeatedly, she built a library of code chunks, like calculating a sine wave, that could be called into action by a single operational code. She standardized these routines and gathered the dispersed operational knowledge of the machine, publishing a comprehensive text that served as the world's first computer programming manual. Hopper's work on machine-independent languages proved that the versatility of a computer is defined by its software, allowing the same hardware to be reconfigured for entirely different tasks through code alone. The Harvard Mark I operated at a computation speed of 3 Hz, 3 cycles per second. Modern microprocessors operate at billions of hertz. The physical materials advanced rapidly. The mechanical gears and relays were replaced by vacuum tubes, then solid-state components, and eventually the magnetic core memory used in the Mark IV. Despite these material upgrades, the architectural principles remain identical. Every operation still relies on separated memory pathways, reusable software subroutines, and the rigid Boolean logic of the ALU. The invisible architecture processing every tap and swipe on modern devices was shaped by the physical and military demands of the Second World War. If you want to continue decoding the hidden systems that power modern technology, subscribe for more deep dives into computer organization and architecture.